For the first lecture of Clément Hongler's mini-series on discrete lattice models.
Okay, good morning. Yeah, I'm sorry I couldn't make it before. Had some exams. Anyway, so discrete lattice models. So what is a lattice? Well, for us, a lattice is going to be a planar lattice. And for the purpose of these lectures, we are only going to look at two lattices for the sake of concreteness and also because it's helpful at some places. So, lattices are very simple things. So for us, either we will look at the square grid or the honeycomb lattice. So, discrete lattice models is a bit redundant a name. So, say lattice models. What are lattice models? For probability people, let's just say that a collection of random variables that live on the graph, either on the vertices of the graph, or on the edges of the graph, or on the faces of the graph, and that the dependence between these random variables is encoded by the graph structure. Okay, so the goal of this lecture is to give a list of maybe 5 or 6 different lattice models and to just define them and to say one interesting fact about each of them. Okay, and in the next lectures we are going to focus on 2 basic models. One is percolation and the other is the easing model, and we are going to prove some results about these models. Okay, so that's the plan. So let's give a small list of lattice models. Well, probably the simplest lattice model is the simple random walk. On Z2. So what is it about? Well, you start at 0, 0, and at each time you jump on one of the 4 neighbors to the point you are at, independently of the past. Okay, so it's a process in discrete time, say. And so that's one of the simplest lattice models. As you probably know, this lattice model, once renormalized in the right way, converges to the Brownian motion. So one fact about simple random walks on Z2. So a fact, a theorem, which we are not going to prove, but it can be proven with SLE techniques that Vincent is speaking about. I hope I stated correctly. If S is a simple random walk from 0, 0, and S tilde is an independent simple random walk from, say, 0, 1, so 0, 0, okay. The probability that S0n, so the set of points that the random walk has visited up to time n, doesn't intersect, say, the set of points that the other random walk has visited up to time n. So obviously, this probability is decreasing in n. And so the actual question is, how fast is it decreasing in n? Well, that's a theorem. It's not an easy theorem, but it decays like a certain power law as n goes to infinity. And so this exponent is 5/8, and that's a theorem of Lauder, Schramm, and Werner. Okay, so I just gave this example because it's the simplest example of a lattice model. Let's look at a simple example of another lattice model. So the collation on the triangular grid. That's the name you will find in the literature usually. It's the same as faces of honeycomb grid. Okay. So what you do? Very simple. So each hexagon. So these are the hexagons. Each hexagon is either black, which means white on the board. Huh? That's always a problem. Okay, so that's black. Or white with probability p, a number you fix between 0 and 1, independent of the others. So it's a random coloring of the plane, if you wish. Yes?
Where's the probability of which event?
Okay. So it's black with probability. Okay, that's thank you. So it's either black or white with probability p and 1 minus p, independent of the others. Okay? Thank you. Okay, sorry.
On the left board, you write probability of that two random walks intersect and not intersect. It should be not intersect, right?
Yeah. Okay. Sorry. I said it decrease. I mean, yes, the probability that they don't intersect decreases, and decreases like that. Thanks, Sasha. Yeah. Sorry. Also, yeah, please don't hesitate to interrupt me if you have any question or remark. Yeah. So okay, so here you have random coloring of the plane. So for each hexagon, you toss a coin, and with probability p, you color it in black, and probability 1 minus p, you color it in white. So what is an interesting fact we can say about this model? Well, first thing is that we can look at the question: what is the chance, given a value of p, that there exists an infinite black cluster? Okay. And so, well, that's a result of Kesten, is 0 for p less or equal than 1/2, and bigger than 0 for p, not bigger than 0, equal to 1, for p greater than 1/2. Okay. So now we can say something a bit more precise, which I think is quite interesting. If you ask the question, okay, so if p is greater than 1/2, there's an infinite cluster with probability 1. Actually, it's unique. There's a unique infinite cluster. Now you can ask the question, okay, what is the chance that a given point is in that infinite cluster? Okay, that's not 1, because first, the point has a finite chance of being a positive chance of being white. So it's not 1, and it's kind of intuitive that it depends on p. And so we can look at this quantity, the probability that, say, the origin belongs to infinite black cluster. Okay, so that number should be 0 for p less or equal than 1/2, and it should be positive for p greater than half. It's easy to see. So an interesting result, which you can obtain by combining results of Smirnov, Lawler, Schramm-Werner, and Kasten. It's a paper of Smirnov and Werner, but it's a combination of these key ingredients, is that you can say that, okay, this goes to 0 as p goes to 1/2 from above, but it goes to 0 at that speed. Okay? So that's a result. Okay? That was the second model. Third model, Ising model. So again, for each of these models, I choose a lattice. Well, the goal is to alternate between square and hexagon. You can consider all these models on the other lattice. Sometimes you cannot prove the results, but you can certainly always consider the models on, essentially any reasonable lattice. So, Ising model. What is the Ising model? So that's a bit harder to define. It's not very hard. So first, define it on a graph, on a finite graph. Okay. So first, G with vertices V and edges E. So what is the definition? So the idea is that on every vertex of the graph, you put a +1 or a -1. So it is a random assignment. Sigma vertices from the vertices of the graph to +-1. And so on every vertex you put a +1 or a -1, and the probability of a given realization is proportional to exponential of -beta h, where beta, the positive parameter. If you want to have a clear analogy with thermodynamics, is essentially the inverse of the temperature. And h of sigma is the energy of the configuration, which is defined as the sum over all the edges of the graph of minus the product of the spins at the endpoints. So you sum, so you have a collection of +1, -1, and to determine what is the chance of seeing that very collection, you take the exponential of -beta times the energy. Beta is a positive fixed parameter, and the energy is of a configuration is defined by summing over all pairs of adjacent vertices minus the product of the values of the configuration at these vertices. Simple example, you have 1, -1, 1, 1, something like that. What is the energy? You're going to sum over all the edges, okay? And what are you going to sum? Minus the product of the spins at the endpoint. So here, for this edge, we have a 1. For this edge, we have a -1. For this edge, we have a 1. For this edge, we have a 1. And so the energy here is just 0. Okay? Or maybe I'm not adding numbers in the right way. Could be. Yeah, it's 2. Okay. Doesn't matter. Okay. So what is this model doing? Well, it's favoring local order. Because whenever two adjacent spins are the same, they decrease the energy. And whenever they are opposite, they increase the energy. So now what you tend to do is you tend to penalize higher energy configuration because of the exponential of minus beta h. And how much you penalize this depends on beta. Okay? Depends crucially on beta. So that's what the model is. Now the question, well, there are several questions. One is what is it supposed to model? Well, it's supposed to model anything that has, a local alignment phenomenon. Initially, it was introduced to describe ferromagnetism, but you can describe many things with that. So, okay, that's the definition of the model. So we have defined it only on a finite graph because, we want. I mean, this definition does not generalize, obviously, to infinite graphs. It can be generalized in some cases, but a priori it's only on finite graphs. Now let's say something interesting about the Ising model on Z2. So the way we are going to understand the Ising model on Z2 is by considering a sequence of graphs that discretize a finite domain of the plane. So now let us take G to be a graph omega delta, where omega delta is the intersection of a domain omega of the plane with the square grid. Yeah, let me just make a picture. You take a domain, you discretize it by a square grid of mesh size delta. This gives you a graph, and you look at the Ising model on that graph. So now question is, what is the interesting thing you can say about large-scale behavior? I mean, most of the interesting things in statistical mechanics are about large-scale behavior, because first, these are the scales about which we can say something simple and non-trivial, and second, because these are the scales that actually matter when you try to understand real world in terms of its microscopic nature. So what is the result we can describe? Well, let's look at the Ising model with plus boundary condition. So we can think of this domain as a window. So in principle, we'd like maybe to study the whole plane, maybe not. But we can think of this domain as a window on a possibly larger system. So the fact is that this model has nearest neighbor interaction because all the energy terms are made of the edges. So if you want to understand what happens outside, you just need to understand what happens on the boundary. And so we can understand essentially everything if we can understand the model with boundary conditions. Okay. So what kind of boundary conditions? Well, for this introduction, I'll just take plus boundary condition. So it just means that I force all the spins outside of my graph, or on the boundary of my graph, that's the same, to be plus 1. So and what am I going to look at in this model? Well, a natural question to look at is, I fix a point here. Let's call it x. So a vertex well inside the domain. And I'm going to look at the expectation of the value of this spin in my discretized domain with plus boundary condition and at temperature beta, at inverse temperature beta, okay, at value of beta fixed. And I'm going to ask the question, what happens as delta goes to 0? Well, and the answer is a bit analogous to what happens in percolation. So for beta smaller or equal than beta critical, I'm going to converge to 0. And for beta greater than beta critical, I'm going to converge to a quantity that is positive. So everything can be computed. So beta critical is log of root 2 plus 1. Okay. So that's Untitled, the result of the 50th. M of beta can be computed exactly, but I don't remember the formula, I just remember the asymptotics. So it's beta minus beta critical to the power 1/8. That's Untitled-Young. So that's already quite interesting. If I want to cite a recent result about this question, I can cite my result with Dimachelkak and Kostya-Dzurov. So at beta equals beta critical, what do we have? We have that this goes to 0. So goes to 0. Like some constant which depends on the domain and on the point x times the mesh size to the power 1/8. So it's a bit different. This 1/8 happens to be the same as that of 1/8, but somehow they are not the same. Whatever it means, they're not the same. So here it's a different question. You know, you fix beta to be exactly beta critical, the last beta for which you go to 0. And you ask, what is the speed at which you go to 0 as you make the graph become finer and finer, as you make the graph become bigger and bigger in terms of number of vertices. And so the result is that at this place, what you see is that you go to 0, like the mesh size to the power 1/8, and with a constant that can be explicitly computed, and which is a geometric term which depends on the shape of the domain and on the position of the point. So I can say what C omega x is. C omega x is a constant times, so this constant is absolute in the sense that it doesn't depend on the domain and the point, times derivative of a map, phi prime of x to the power minus 1/8, where phi is the unique conformal mapping from omega to the unit disk that sends x to 0, and that has positive derivative at x. So I kind of assume that you know what conformal maps are, this because Vincent is teaching SLE. If someone wants a definition or a reference for this, I'm happy to give it. But I assume that it's kind of been seen in Vincent's class. So, well, okay, so this exists by Riemann mapping theorem. Okay. Okay, so it's fairly explicit. So that's a result of Chelkak and Dzurov. And I can also say that this constant can be computed explicitly, but somehow I don't want to speak too much about that one. Okay? Okay, so that's another model and another collection of results. Let's go to yet another model. So, number 4, dimer model. So, what is a dimer model? We're going to look at the dimer model. Again, we choose a graph, and for the purpose of this talk, we'll choose the hexagonal, the honeycomb lattice. So you take a finite graph, okay, and a perfect matching or dimer tiling of the graph of G. What is it? It's a collection of edges of the graph such that every vertex belongs to exactly one edge. Okay. Is a collection of edges of G such that every vertex belongs to one edge. Exactly one edge. So it's a matching in the sense that you're marrying pairs of vertices. And it's a dimer, and it's called a dimer tiling because we can think of, you've all heard of polymers, which are long chains of molecules. A dimer is like a polymer, but with di for two. So it means that you're just binding two molecules that you imagine live on the grid. So how does it look like? Well, if I draw a graph like that, perfect matching, dimer tiling, it's a collection of edges like that. So it's a sub-collection of the collection of edges of the graph, such that every vertex, if I didn't make a mistake, belongs to exactly one edge. Okay. So what is the dimer model? Well, in the simplest variant of it, just take one dimer tiling uniformly at random. Yep. So now the question is, how does a large random dimer tiling look like? And a priori, it's not exactly clear, how one should describe what one sees here. And as a matter of fact, there are many things one could do, but there's a particularly nice thing, which is to draw rhombi surrounding the edge you selected. Very visual. Okay. Okay. And now the nice thing is that it looks like a 3D surface. Okay. So, how to describe large scale. Well, so draw rhombine around edges. Yeah. It looks like a surface in 3D. Do you see it? Huh? This looks like the boundary of stacks of cubes. And of course, I didn't draw things in a super regular manner, but I hope you can see that one could imagine that there are like stacks of cubes. Like I imagine 2 cubes stacked here, 2 cubes stacked there, no cube here, and it looks like a 3D object that can be completely described by its surface. Yeah. And okay, so now we have, the nice thing is that if you do this, you have a random field. Because you could look at the height of this surface. Well, I want to mention just 2 results in an informal manner about this. The first is a theorem which says that, okay, if we discretize a big hexagonal domain, at large scales, we see something like that. Okay, I don't want to define too much, but so basically, if you discretize your large hexagon into many small hexagons, and you take a dimer tiling uniformly at random, how it will look like, so how a typical dimer tiling of this domain looks like, is the following. What you will see is a random surface where the area inside of this inscribed circle looks really random, and on the boundary, things look very smooth. Okay? They look highly ordered, non-random at all. So that's a theorem of, but that's not really stated in a loose manner. We see an Arctic circle. So it's an Arctic circle is something I just described very informally here. So we see a boundary between 2 phases, one disordered phase and one ordered phase. So it's a theorem of Cohn, Kenyon, Prop. There's also Kenyon-Lokunkov, I guess, to generalize this kind of thing. Okay, so that's one result about dimers, and another result about dimer I want to state very loosely, without any detail in the statement. It's partly a theorem, partly a conjecture. So mostly of Kenyon. It's that the fluctuations of the heights are described by a Gaussian free field. that Jason is speaking about. Okay? So the goal is not, we are not going to speak about the diamond model anyway. The goal is just to get you interested in this kind of business of lattice models, to explain why it has connections with other subjects. Okay, 2 more models to go. Uniform spanning tree. That's also a model we will not speak about, but it's just relevant as an example of a lattice model. And there's a simple result that everyone can understand. Happy to mention. So, so what is a uniform spanning tree? What is a spanning tree? A spanning tree of a graph is a tree contained in the graph such that every vertex belongs to the tree. So it's a subset of the edges where you have just enough edges to make the graph connected, but you don't have too many, so you don't have any cycle. Okay? And uniform spanning trees, that's a model, so you take just a random spanning tree uniformly at random. Okay, so take a spanning tree of a graph uniformly at random. So now let's just take, say, I don't know, a big square, a subset of the square grid. It doesn't need to be a nice square, it can be anything. But okay. And, okay, so a theorem which has 2 main kind of proofs. One is of Kenyon, and the other is Lola Schramm-Werner, plus some people who contributed to making this precise. So, very simple question you can ask. Okay, now you take a point x here and a point y here, far apart. Okay, and you ask the question. Okay. So what is the length of the unique path that goes from x to y? Okay, so take x, y in the, say, discretized domain. Okay, and you ask, okay, what is the length of the path that goes from x to y in the tree? So you know it's a tree, so there's a unique path between any pair of points. And so you can ask the question, okay, you know, okay, how many edges do I need to go from one point to the other? And the answer is that it depends on, so with high probability, this length behaves like 1 over the mesh size, so the size of a little square, to the power 5 over 4. So it's not quite as short as a straight path, but it's not so long. Okay. One last model to conclude this short overview. Self-avoiding walk. Also sometimes known as the self-avoiding polymer, of the hexagonal grid. the Hardingham lattice, same. So what is it? So no. Very simple. Take a walk of length n that doesn't pass through the same vertex twice. That's why it's self-avoiding, okay? So you have a finite number of such walks, and that's a model that people study a lot. It's a recent theorem. It's Hugo Duminil-Copin. Smirnov. It says that the number of such walks so it's not really a probability result per se. It's more a counting thing, but it's very close. The number of walks of length n behaves like square root of 2 plus root 2 to the power n. Okay. And there's a conjecture that there is an n to the power 11 over 32 correction. And somehow this is mostly this exponent that got people interested in that model. It's still a conjecture, but you know, it's already very interesting. We have part of the conjecture proven. Okay, so this is just a collection of models, and I hope I didn't get you too bored. At least, well, I'm sure I got many of you very bored, but I hope that at least I gave an interesting result about each of the models. These are really, I think, the reasons why many of us studied this field, because they were like very simple results that seemed to contain a highly non-trivial amount of information. And I think that everyone agrees on that. That these models, they are very, very simple. The questions we ask about them are very simple, but they contain, numbers that show that there is something really deep hidden behind them. Okay, so now let's make some general considerations about what's happening here, and it will tell us, a direction where we can go for the next lectures. Okay? Any questions? Yeah.
Which part of the conjecture is proved?
I mean, it's well, okay. Okay. So the number of walks of length n, of course, you cannot write exactly what is this number with a closed formula. I mean, not of course, but it turns out you cannot write a closed formula for this, but you can look at the asymptotics, how it grows as n grows. Okay. So it grows exponentially fast, and that's the order of the exponential growth. The interesting thing is that this exponential growth, well, now is known, but there's a polynomial correction to it, and it's it's of an interesting power, 11 over 32. So to put things in a bit more perspective, the idea why people are so interested in this is because this is dependent on the nature of the lattice. For instance, the corresponding number for the square grid is not known. It's probably not an algebraic number. However, the corrective term does not depend on the choice of the lattice. Well, it's not so surprising if you think about it. If you know something about, say, Ising model. For instance, for Ising model or for percolation, there's a critical value, beta critical. For percolation, I didn't state it explicitly, but this was the 1/2. So those numbers, they depend really very much on the choice of the lattice. However, once you tune your parameter to be exactly that one, what you expect is you expect to have continuum model in the limit. You expect to be able to renormalize your model in some manner, and that this renormalized model converges to a universal limit which does not depend on the choice of the lattice. And as a matter of fact, what happens here is that basically if you decide to weigh your paths using this kind of thing, you should converge to an SLE process. And this 11/32 can be seen in the SLE, been done by Lola-Schramberger. So it's not so surprising that people are interested in this one, because this is supposed to be the universal term. Okay. So how this result is the analogous of computing the beta critical for Ising model. Yeah. Okay, I stated it in this way because it looks much more elementary stated in this way, but that's really what is behind. So, okay, now what can we say? What are the common features about these models, except that they have simple, non-trivial results that can be stated, and now they can be proven also, and except that there are some funny numbers appearing in almost each of the statements. So the common features of these models is that they are critical. So what does it mean? It means that they exhibit long-range fluctuations. Well, a priori, they don't all exhibit that, but that's really the case of each of them. So for the random walk, it's kind of clear that there is a scaling limit, and that the scaling limit, if you look at the picture from far away, is random. So the model obviously has long-range fluctuations. The percolation, well, what does long-range fluctuation mean here? Well, I'm going to tell you something really informally, and we are going to accept that this means long-range fluctuation. The idea is that if you look at very low value of P, so very, very few black hexagons in your picture, what you have is that, of course, you have no infinite cluster of black hexagons, but moreover, if you look at these clusters of black hexagons, they are really, really small, and the probability of having a cluster of black hexagon of size larger than n decays exponentially fast in n. Okay. Now you can ask, okay, what happens for a very large value of P when you have lots of black hexagons? Surprisingly, it looks a bit like when the chance of having a black hexagon is very small. Having a lot of black hexagons is in some sense very similar to having very few of them. So, what happens there is that we know we have an infinite cluster of black hexagons. But now if we look at things that are not in this infinite cluster, so if we ask the question, what is the chance that a black hexagon is in a finite cluster, okay, of size n? Then this chance also decays exponentially fast with respect to n. And as you move the chance of having a black hexagon, as you move this parameter p closer to 1/2, this chance becomes bigger and bigger. The chance of being in a finite cluster of large size becomes bigger and bigger. And actually, when you reach exactly this point 1/2, that's exactly the case that the only case where the size of being in a cluster of black hexagons of size n decays like n to a polynomial, like a polynomial in n, not exponentially anymore. It decays like n to the power -5 over 48. Okay, so there is something special that happens for percolation at the very point where the chance of having black and white hexagons is 1/2. And you can really ask questions about long-range fluctuations. If you are above p equals 1/2, you have a large cluster, but that's not really a fluctuation. What happens at p equals 1/2 is particularly interesting because you have something that's macroscopic, but at the same time something that's random. Okay, so that's what I mean by long-range fluctuations. For Ising model, it's very much the same story. So for very small value of beta, for very small nearest neighbor interaction, basically you see a completely disordered picture. For very large value of beta, you see a completely ordered picture. And the fluctuations within that picture are negligible. The only case where you see long-range fluctuations, where you see some, randomness arising at large scale, is the critical point. Some models are automatically critical. So the simple random walk is automatically critical. The diamond model is automatically critical, at least defined in this way. The uniform spanning tree, the same. And the self-avoiding walk, I didn't really define it as a statistical physics model. The way I defined it was really in order to make the statements as simple as possible. But the idea is here you can say, I want to look at random walks of non-fixed length, but I want the probability of a random walk to depend on the number of steps it makes. And if I choose the probability to be like this, depend on the number of steps like that, then I get a model that is critical, okay? So if probability of a walk, if I define it to be proportional to this, then I get a critical model. If I take this number to be smaller or bigger, I don't get a critical model. So each of these models is critical in the sense that it has long-range fluctuations. So now where does this bring us? Let me first write it, but where does this bring us? That the models have long-range fluctuations. So all the cases we discussed are critical, or they have a critical phase. Means long-range fluctuations. And of course, if you do probability, you lack fluctuations. This is the interesting thing, because that's what is random. So if we have long-range fluctuations, we can hope we have macroscopic random objects. So we can also hope that if we look at the model from far away, we can renormalize them into continuous random objects. So the large-scale pictures becomes continuous a random object. Okay. Okay. So what do I mean by this? So first, it's not a statement, a mathematical statement, that if you have long-range fluctuations, you can be described by a continuous random object. Yet it is something that is, empirically true. I mean, for all the natural model we look at, whenever they have long-range fluctuations, they can be described by a continuous object. And so now, a natural question, and that's really the question I want to address, is that, okay, so if we're supposed to have some continuous things in the limit, what are those things? Well, as you guessed, probably Esterlys or random fields, such as Gaussian free field. So by random curves or random fields. And now really the question I wanted to address in the next lectures is, okay, what are the techniques we have to make sense of this? So really a key question in this business is how you connect these discrete models with their continuous limits. because they seem to have continuous limits because they have long-range fluctuations. And so how can we understand this connection between discrete and continuous? How can we understand that the collective random interactions yield some collective random interaction at the macroscopic scale, and that these objects can be described? Moreover, you've seen that SL is an extremely precise object, so how can we possibly connect a model like percolation or Ising model with SLE? So, you know, there are many techniques one can use. They fall into different categories. But in the end of the day, you really have to connect discrete with continuous. So you really have to find something that lives on the discrete level, and for which you're going to be able to say, well, okay, here is the mathematical statement that tells you that this discrete thing converges to that continuous thing. And there are not so many techniques for that. So what techniques do we have? For random walks, how do you prove that that the random walk converges to a Brownian motion? Well, there are mainly two steps, you know. One step is to make sure that the path doesn't behave in a crazy manner. That the path is, you know, has a chance of having a limit. That its fluctuations are not too wild for you to have a limit. So you need some estimates. And the other part is how you identify the limit as being Brownian motion. Here what you use is you use central limit theorem. Okay? And how you prove central limit theorem is using characteristic functions, usually. I mean, there are several proofs, many proofs of central limit theorem, but, you know, raise something here that we know about how things converge to Gaussian. Now, the question is, will this help us understand the limit of Ising model? And the answer is, I think it will not. Okay? So, what other technique can we use to make sense of this? And, well, there is one technique which we're going to speak about in these lectures, which is discrete complex analysis. So that technique is specific to two dimensions. Okay? But really, if you want just one small message about how the discrete is connected with the continuum, just think that we'll have a definition of discrete holomorphic functions. So holomorphic functions living on a lattice. And these will turn out to be relevant for our models. And on the other hand, we can develop a theory of discrete holomorphic functions and prove that discrete holomorphic functions, if they are not too crazy, converge to continuous holomorphic functions. And we can hope that once we are there, we are already in the continuum, and we can work with things defined in the continuum. So that's really going to be a way to pass from discrete to continuous world, okay, to connect a model with the discrete complex analysis, to let the discrete complex analysis bring us to the continuous complex analysis, and then to understand the limits in terms of the continuous complex analysis. Okay? So I'm going to stop now because I need a 5-minute break to prepare the next lecture. But if there are any questions, I'm happy to answer right now. Yeah? Yeah. Okay, thanks.
Yeah.